Yeah, of course I'm recording it. It's because 25% of our class is missing. I can't just let them not.
Please cut this part. It's really good. And let them know how much
Make sure.
disregarded.
Yeah, versus. Oh, I don't know if they can see
I took a picture. I
there.
can email
Oh,
you.
okay, good. So if
I
you can't
changed-
see all of Becca's mostly was invalid. Let's go with invalid arguments.
I changed number 3 so that way I can't get in trouble because you can't actually assume what I'm saying.
Yeah, that's a good idea.
We have,
It
like,
could be anybody. It could be
other-
almost
the other teacher.
anybody. Okay, so we have talked about already 3 different approaches to looking at how things change motion, right? So this isn't on this slide, but we have this idea of states and transitions between states. We looked at this mostly when we were doing kinematics, and we had like, the ball in a tree, and then you drop the ball, right? So state 1 would be where the ball is at the beginning, and state 2 would be the ball like hitting the ground or something. And then we had acceleration causing the transition between those states. But we now know, and you probably knew before, but now we've officially studied the fact that that acceleration is caused by forces. And so we've seen how the net force leads to an acceleration, and we've seen how acceleration in one dimension, but still, acceleration can be used to calculate, the changes in our position and velocity and whatever. So this is one approach for looking at transitions of state. There are 2 others, and they're fundamentally, at the base level, the same thing. And you can use calculus to go back and forth between them. It's a little harder if you can't do if you don't have the calculus toolbox specifically for it. But another approach is the one we looked at on Monday, which is we have this quantity called momentum, right? It's mass times velocity, and we can see how that momentum changes if you apply a force for an amount of time. We're going to look at one more way to transition between states, where in this case, the states are going to be represented by different kinds of energy. And we're going to have a quantity called work that tells you how that energy changes.
I'm fighting the urge to quote Hamilton. Actually, it's
Yeah.
You watch
Peggy.
You watch.
It's funny because it's the only time Peggy comes up.
In the timeline, she would have died between right between Act 1 and Act 2 from there's dispute whether she died from tuberculosis or suicide.
It doesn't matter. She wasn't one of the important Schuyler sisters. So
He wasn't in love with that.
exactly. Just 2/3 of the Schuyler.
Witches. In fact,
Exactly. Yeah. Excused. An excused absence.
Jack, get out.
Come up with an excuse reason to leave.
Come up with an excuse to class right now, you and okay.
But that's not 2/3.
What?
It'll be 3/7, or approximately 35%.
Oh, 42%.
Oh, 42%. Oh, dang it. Yeah, it won't be enough. Okay, so we're studying these. I'm trying to give a context where you can see that these are similar, right? And in a practical sense, you would determine which one to use, basically based on what specifically I ask you. And that will become clear once we actually talk about this last one. If you were doing physics out in the wild, There would be additional factors that you might choose also. A lot of those are kind of more advanced than what we would normally talk about in this class. Things like symmetry. Symmetry is an enormous aspect of physics that we just kind of ignore in this class. But that would be
How much of physics becomes just like irrelevant if you are like wrong if you actually take into account a lot of most of the things we ignore?
so so there's a philosophical versus practical distinction in that question. So a mathematician would be pretty upset with, in fact, some mathematicians have been famously upset with the things that physicists do in order to get measurable outcomes. But in most cases, the types of problems that physicists pose and solve, you get very good answers by doing it basically the way that we're approaching it. With, adding in the differential equations that we're definitely not doing because that is just outright calculus all over the place. But that's just because of a math thing, right? That's not a fundamental thing that we don't include in this class.
But like air resistance.
Yeah. Yeah, so again, the context of the problems that I'm giving you, 80 to 90% of the time are ones where it's reasonable to neglect those factors, and you could estimate the amount of error it would give you in the outcome. Eventually, it does become an engineering problem, right? So, like with air resistance, we had all those drag coefficients, right? There's no great way to derive the drag coefficient for a Lamborghini. Right? So it becomes a factor of measuring it. And if you want to get in the weeds with drag, there's more than two forms. We kind of look at the endpoints of two different forms. There's this quadratic form that we used. There's a linear form that we don't really do in this class, but sometimes we do in physics too. And so that would be like something in water would experience the linear, so it would just be proportional to speed, not speed squared. In reality, there's a continuous variable in between water and air. You can make a fluid by changing things like temperature and pressure and whatever. You can make a fluid anything in between air and water, basically. So drag can get very complex in what we might call like medium Reynolds number regimes.
So pretty much it's just too complicated for us right now.
For that one's too complicated for anyone, and you just let an engineer measure it, or honestly simulate it in a computer, and then or let mathematicians not give you any answers, but help you. So in Michigan, I was in the math department for a while, and I had to explain to people that I was doing very applied mathematics, because applied mathematics just means something that someone in principle could use to do something with. And not that they were doing something with it. They were making the math that somebody could in principle use or something. So since I was modeling and simulating and doing things with math, I'd have to be like, no, we're not. You're like a level of abstraction still above what I'm doing. So I can't remember if I showed this diagram last time. So this is an analogy that we can draw when talking about things like energy, because energy is a very abstract idea that somehow we can apply exact numbers to, but defining what it is starts to get suspect outside the context of, an actual calculation to be done. So excuse me, the analogy is comparing it to money. And this works fine as long as you don't think too hard about what money is. If you don't think hard about money, then you can think of, okay, well, I've got some amount of money that might be zero. Let's not worry about that at the moment. You've got some amount of money, and maybe it's in cash, or maybe you have stocks in your name or something. Maybe you've got a Steam wallet, maybe you've got a checking account. I don't know your life, but in principle, these might be places where you have money. And if that amount of money changes, it's because you either got some more money or you spent some of the money or lost some of the money. That money could have been taken from you. I don't know, but there's like money in and money out is the only way that the amount of money you can have can change. Okay. Whereas things like interest in your savings account would count as income, stuff like that. Depreciation of stocks you would have to call expenses, which is literally what you do if if you are doing a balance sheet of your assets or whatever.
I mean, that's like physics rules only work on Tuesday and bank holidays, and like in this very specific niche environment that would like never actually happen.
I have not.
No, okay. Well, they exist. I've always been like, huh, that's funny, and now I realize how true it actually. Given these 16 variables, if they were there.
So here's the other end of this argument, right? We are biased because we live on Earth and we have all these things on Earth that we have to do. Physics applies well, I mean, yeah, right? So physics applies on the scales, 10 to the 15 times smaller than a human, up to actually way more than that, 10 to the minus 35. So, 0.001 times a human size, all the way up to the size of the galaxy, which is 40 billion light years, which is, I don't know, a lot. Yeah, let's just go with a lot. So we have this enormous range of scales, right? And it's just because we're biased by being living beings in a certain aspect of those scales, where the complexities of the actual interactions make it harder to calculate any one particular scenario, right? Because you're interacting with like 10 to the 25 particles right now just sitting there. That's a lot. That's probably a lot for a computer to calculate. So, in a sense, you're right that there are practical limitations to computing things on human scales. But that's not physics' fault. It's the fault of the number of things you've run into. Run into fewer things. Try to run into only like 10 things. This requires being pretty small for only 10 air molecules to hit you, for example. So this money idea, right? We've got the system, which is assets that you've got. We have these transformations inside the system, which is like you use some of your cash to buy some stocks or whatever. I don't know, right? But you can move money back and forth between assets that you have. And also you can have transfers by having income or expenses, and that will change the total amount of money you got. Okay, so energy is a lot like that, and I guess I'll go ahead and look at the next slide and then come back to this one, where you've got a system, you have a bunch of different types of energy inside that system. Kinetic is one type of energy that we've talked about already. But you can also have chemical energy, you can have thermal energy, you can have different kinds of potential energy. We'll talk about that more in a second. But if you want to change the total amount of energy in your system, it's going to be because more energy comes in or some energy goes out. I'll say more about that, but let's come back and talk about the different types of energy. So this one is the one we've already talked about. It's the energy contained in a thing moving. This is our kinetic energy. I'm going to write some things out. What? Oh. So we have K is, where are you? K is kinetic energy, which is energy stored in the motion of an object. And then the next two examples are a U with a subscript G and a U with a subscript S. These are both types of potential energy. So there's more than just those two kinds. In general, potential energy is energy stored in the position or arrangement of objects in a system. And we have two specific kinds. We've got UG,
Gravity.
which is potential energy of gravity. Yeah, I'll put the gravitational in front. Why not? Gravitational potential energy. And
But the other one, like that.
exactly, yeah.
That's where the bow and arrow comes in.
Yep. The S stands for spring. I kind of don't love the notation, but that's what we've got. Because they don't have to be literal springs, right? You can think of the arms of a bow as a spring, but they'd be what we call a cantilevered spring, which is not what people normally think of when you say spring. But they are definitely storing elastic energy because they're, the one side of the arm of the bow stretches while the other side compresses, and it wants to go back to its original position. Well, okay, yeah. So there might be actual springs in some cases, and
So that's actually kind of bring up a question. So relating to archery, so the compound bows, they use these like the cams that go to the top. Would that still count as like elastic energy? So I guess you're
Yeah.
stretching the string now.
it's not the string that's literally stretching
No.
in bows, in real bows, little toy
Yeah.
bows.
Because the recurve, you're actually bending the wood. I get
Mhm.
that, but as far as the compounds, those cams spin. Unless they don't release, when you release, they spin back.
Yeah.
Would that
So
still be elastic?
yeah, because there are springs in the cams somewhere. Uh,
Oh, in the middle.
yeah. So I guess with compound it is a literal. Well, they're all springs, but it's more like a spring like you normally imagine with a spring. And the height of an object, at least in terms of the way we're going to be using it. And then, spring or elastic potential energy is the energy stored in the stretch or compression of a spring. And I'm going to add, because there's other types of springs, or torsion, or bending of a spring. What's it?
But enough potential energy to slice it to put their pinky out.
And let's see. So this one over here, we've got our thermal energy, ETH. We are going to make a little bit of use of this. You use it a lot more in thermodynamics, which is kind of implied by the name. This is energy stored in the temperature of something. So ETH.
So that's like when something heats up, it's like boiling, you get the atom, so move.
Exactly.
But
Um,
the energy.
That's exactly right. And it is literally the total of the kinetic energy of all the particles
Oh.
vibrating. I'm not going to put that here just to avoid confusion, but that's is indeed what it
I
is.
guess I never thought about how much physics actually overlaps.
Yeah, I mean, it's foundationally just and thermodynamics, I don't feel like chemistry should claim thermodynamics because it's a physics thing, but whatever. It's fine. Fine chemistry. Uh, what I was, oh yeah. In this class, the temperature changes are usually due to friction or collisions. Yeah, so things also change temperature if you squish them. I actually have kind of an objection to looking at collisions as a change in thermal energy. It's not wrong, but I think there's a better way to talk about it. But I'm not going to because no one else does, so we'll just call it thermal energy. Why not? Let's just do what everyone else does. And then we have chemical, and I'm putting another example of one specifically because we're not going to use it, but I want you to just see there's other types of energy. There's a whole bunch of different types of energy, and we're not going to be using most of them. And our equations are still going to work in cases where those aren't relevant, right? So, chemical energy stored, well, this is a delta, right? No, they don't use delta here. In the bonds, so atomic and molecular bonds, I'll put it that way. In atomic or molecular bonds. Whereas nuclear, this is the energy stored in, what do you think? Yeah. So it's in the nucleus of an atom.
So that's like, this makes me sound really stupid. So like atomic or like nuclear bombs, it's then splitting an atom. So it's releasing that nuclear energy from inside.
Exactly. Oh, that's great. Okay. So these are only relevant if these bonds change, right? We are sadly not allowed to conduct experiments where the energy stored in a nucleus is changed. So we will not see any systems where there's a change in nuclear energy. We aren't going to actually do outright any examples where there are changes in chemical energy. In a lot of cases, that would be a chemical reaction, but organisms cause changes in the energy in their environment, ultimately due to changes in chemical energy internally, right? So metabolic energy lets me lift things, right? So I've got the ATP being reduced to ADP, and that releases energy, and my cells use it, et cetera, right? So that is a chemical energy change. I think I said everything that's important. So we will incorporate this in kind of a conceptual way, but physics class, we're going to be sticking primarily to changes in physical types of energy. And that actually reminds me, I went to introduce one more term, which is mechanical energy, the total of kinetic plus potential energy. This is a convenient term, and I'm going to write it out in using all of the potential energies that we've got. Because we're going to see cases where mechanical energy is conserved, which is when you add kinetic and potential together, that total amount of energy is a constant. And it's convenient just to have one word for all of that. Okay, so actually, I guess before I go to the next slide, I'll go ahead and define the next couple of things. So we talked about how energy can enter or leave your system, and that would change the total amount of energy in your system. So we have transfers of energy, and we have two types of those. We have work, for which we use the letter W, and we have heat, for which we use the letter Q. And at this point, you just give up hoping that letters have anything to do with the words. And this is the fault of the people who developed thermodynamics. I think it stands for like quantity of energy or something like that. I don't know. It comes from something, but now we're just stuck with it for history. Transfer of energy due to external forces on objects in a system. And specifically what I mean by external is whatever forces we're talking about, the agents of those forces are outside the system. That's right. Transfer of energy due to difference in temperature between the system and its surroundings.
I hate to say it, but I genuinely use agent of the slot term with different agents.
That's pretty great.
Like it goes through my head every time.
Really helpful. Like, does my drawing help too?
Your drawing is more traumatizing, but it definitely comes up in my head.
You know, activating the amygdala is a well-known way to increase retention in the hippocampus of new information. And the amygdala activates under a bunch of different emotional contexts, but especially pain and fear. So
pretty much, if my roommate just like hits me over and over again as I'm studying.
until you get used to it, and then
Oh,
I don't know, it'll stop working.
When people throw something fake. Well, like, there's this thing when someone throws something at someone and they say something, like say, "Whoa!" So like this girl was throwing like anything at her boyfriend. It's like,
Day 42.
so whenever she says the word "girls," he gets really scared and flinches and ducks down.
Yeah, there's one that's like day 42 of training my best friend to be scared of her ex's name, and they'll then James and throw something at him. It's great.
Yeah. Pavlov would be proud.
Do you think these are healthy relationships, Dr. Jack?
It doesn't sound so, but you know, I try not to judge. Okay, so just reflecting back on this image again, we have the types of energy in our system. We talked about these 4 different types, and we also added another. Spring and gravitational potential are both hiding in this U right here. And you might note that a lot of these, the arrows point both ways, but then for thermal energy, the arrows point down and then do not point back the other way. This is because of entropy. Entropy is going to trap energy inside thermal energy.
Oh.
Um, and so that's where that's coming from. We don't worry about the second law of thermodynamics so much in this class as we would in second semester, which I suspect. Is everyone in here? Is everyone in here a senior? No? Oh. Okay. Well then, hey, next year you could take physics 2, and we could talk about entropy.
I thought we were taking that class, but thank you for the offer.
Dr. Munson already tried scaring us into PSA. Oh, PSA.
So, as far as this class is concerned, we are not going to be dealing with heat at all. I'm going to keep it in equations that we write out, and then I'm going to immediately scratch it out because it causes me physical pain if I don't include it in the equation because it's there. But we're not going to encounter scenarios where we need to use it.
Where's the strike through option on Google Docs? Because I can't remember.
Text and then or format text, and then it's like,
Thank you.
oh, the theme change made these extra tiny, but so I'm going to ask you a couple scenarios to think about how these transitions or transfers of energy can take place. And a reminder, a transition is going from one type of energy to another one, and a transfer is work or heat changing the amount of energy. So we've got a kid, and the kid is starting at the highest point of their swing session, and you know now they're swinging back down, and when they reach the lowest point, wait, what? No, they're just like at the bottom as opposed to like, so you're starting here. This is your initial state. This is your final state. Of course, the kid would keep going, but that's the part that we're looking at. So the options for picking a transform of energy is kinetic to gravitational potential to kinetic, thermal energy to kinetic, gravitational potential energy to thermal energy, or kinetic energy to thermal energy. Give you 30.
Wait, sorry, by the highest point of art, does that mean like swing set and then he's like up here?
No, just highest point that he goes, not the highest point possible.
Best
Oh.
part of swinging. Oh no,
I was gonna say,
Those are
normally you
tryhards.
try to go all the way around, don't you?
those are tryhards.
Oh.
You never seen that?
No, I just don't like every time.
Isn't that
I
like
said that scared the crap out of me.
that's the point of swinging?
No.
I thought that was the point. Like you're trying to go as high as you can and then you jump off.
Those people used to
And the point of sliding is trying to impale yourself on something on the bottom.
That's not how we played the
the
playground.
ones who would like spin around until it got shorter and shorter, and then they would stop. I hate those people.
They had to take this
I
picture
did
of the
that,
playground because somebody jumped
They're
off of it.
tryhards.
And broke their
You
leg.
tried to go all the way around if you could.
I was scared.
I have never seen anyone get very close to accomplishing it without outside help, like, but just by kicking. I've never seen.
I've seen
Oh
someone
no,
do it.
no, there was
By
always
themselves.
outside help.
Huh?
There was always outside help.
Oh.
More able
So
to-
there's actually a really good reason why it's hard to go over the bar. Whereas, like, so without falling out of the swing on the way, right? So as you go past this point, right? So past horizontal, right? So gravity wants to make you fall out of the swing.
Right.
So the only way to stay on the swing, obviously you can hold on to the chains, but that doesn't help because the chain will go with you if you
Yeah.
fall. So the only way to go past this point is to be going so fast that your body would want to fly off already if there weren't a seat in the way. Right? So you need if we're going to talk about this more in 2 chapters, you need the centripetal force to still be there to keep you in the seat while you go all the way up. And in order to do that, you need 2.5 times more energy than you would get if you just started horizontal. So it's really hard to kick yourself and then go from this horizontal to anywhere more than horizontal without falling off. So that's why you almost always have to have someone like help.
Have you seen Friends?
Yeah, but like, when it was originally on.
That's disappointing. Do you remember Rachel's like absolute terror of swings?
No.
Okay. She was scared of swings and what
We
I did.
would all be able to swing on it.
I imagine this would be like
I
your origin
love
story
the
to
hot
never
dog.
letting Rosie in
That's what it's called.
Oh no.
I
It
was either doing that.
took Rosie longer. Well, it doesn't matter. Anyway, they like swings. We've got B is the majority vote, which is indeed right. So you're going from gravitational potential energy into kinetic because your height is going down, right? And we said gravitational potential energy was stored in your height. So that is being lost as you get lower, but your speed is going up. And so the energy stored in that speed is increasing. So we have exactly what most people voted. Let's see another situation. And this takes some time to think about this one. So a skier is gliding down a gentle slope, right? This is not a good ski hill. You're just very gently drifting down at a constant speed. And we'll add, actually it doesn't matter. So I don't need to add additional context for that, I think. So we want to know what energy transformation is taking place while they continue down at a constant speed. I think all the options are the same.
Are we neglecting friction?
So that's what I was about to talk about. We don't have to neglect anything for this to work. And in fact, if we neglected everything, it wouldn't work.
Okay. Yeah.
And by everything, I mean friction or air resistance or.
Uh-huh.
Right? So in real skiing, the friction is very low, but you end up going fast enough that air resistance becomes very high.
So it just kind of cancels out.
Yeah, I guess you could think about it that way. You reach a terminal velocity, a terminal speed,
Mhm.
skiing downhill. All right, we've got 5 votes. Let's see what people think. This one is trickier. So a lot of people still voted B, and I get where you're coming from. There is definitely kinetic energy because the skier is moving. But is that kinetic energy changing? No. So there's no further transformation taking place between gravitational potential energy and kinetic. There was at some point, probably when the skier started. It's not definitely true because if someone gave them a push start instead of them slowly speeding up as they went down the hill, then it might have never happened. But it's definitely not happening now because their speed is no longer changing. Why isn't their speed changing?
Terminal velocity, they can't get any faster.
Exactly. So that gravitational potential energy is going somewhere. Where is it going? Exactly. So D is the correct answer here. It's turning into thermal energy, and that's either between the friction between the ground and the skis, or in this case, more likely, the air resistance. So you're heating up the air molecules, technically, not in a very measurable way, but it is happening. And that's where that's coming from.
So it's the work turning into heat.
No, so that is something I meant to specify, so I'm glad you brought that up. We have two things that sound very similar. We have thermal energy and heat, right? They sound very similar, but they are doing different things. So thermal energy is counted in your system, and it's the molecules of things in your system moving around. Okay. And that amount of them moving around isn't really going to change unless you heat it up more, or you change the temperature of it, or you rub it on the carpet and make the friction heat it up, or something like that. I could say it's the energy stored in the temperature of the object. So as long as the temperature isn't changing, the molecules inside your object are moving a constant amount. They're jiggling around with the same average speed, or whatever you might remember from chemistry. Heat is trying to change the temperature inside your system. I say trying because it doesn't necessarily go to thermal energy. It could actually go to any of these things. But it's coming in because the environment's hotter than your system, or it could be going out if your system is hotter than the environment. So thermal energy is temperature, the current temperature of things inside your system already. Heat is trying to change the temperature because there's something hotter or something colder around you.
Wait, so what's the connection between thermal energy and
Formally, what happens is if you were to zoom in and look at every single molecule bouncing around, and this works perfectly for a gas, and it's a good analogy if it's in a solid or water. There are extra things you have to worry about, but it still conceptually works the same. And so if you measured the speed of every single molecule and calculated its kinetic energy with the equation we already know, 1/2 mv squared, but it's the mass of each little molecule times the speed of each little molecule. If you add all of that up, you get the thermal energy. We don't have to have that in our brain when we're doing calculations with it, but that's what's under the hood. And so if you increase the temperature of an object, they bounce around faster, all the molecules, and so the thermal energy would increase. But you can think of, okay, let's think here, mug. In my mug is some water. The water is a certain temperature. Water molecules are all bouncing around all over. So there is an amount of kinetic energy for each molecule. Add all up, you get the thermal energy in my mug. That is directly scales with temperature. It comes from the definition of temperature is the average kinetic energy of the particles in the mug. But we wouldn't say the kinetic energy of my mug is, 500 joules or whatever, because the mug as a whole isn't moving. So it makes sense to separate all of the molecules jiggling around from my whole mug, someone picks it up and starts moving it. So we save kinetic energy for the thing as a whole moving, and thermal energy is all the little molecules moving.
So thermal energy is kinetic energy on a smaller scale.
Yeah.
How does this relate to like Heisenberg uncertainty?
We don't actually need to incorporate it. So we can do, in fact, unless
Because
you're, go ahead.
Heisenberg uncertainty is where like everything's slightly moving at all times, so you can't actually tell
Okay, I see what you're saying.
Am I thinking of the right?
You have the right
Okay.
thing.
Okay.
So, more formally, what's going on there isn't strictly temperature related. It does cause there to be a minimum possible temperature for things. So it is related, just as you're saying, but we don't have to, if you have like a single electron, right? And in chemistry, it's got the electron cloud that it's in. That's kind of displaying Heisenberg's uncertainty principle already, because you don't know where it is, and you don't know exactly what energy it has, pretty well, but you can't know exactly. When we're talking about thermal energy in the cup, though, the not knowing exactly where every molecule is, we don't have to think about it quantum mechanically, because the motion of the particles themselves are going to be much bigger than that sort of minimum motion due to Heisenberg's. So it isn't until my water is getting pretty close to absolute zero where we would have to start thinking about Heisenberg's uncertainty principle to apply it. It's a really good observation. Yes.
Heat is affecting the kinetic energy, but it not.
So that's the way it definitely turns out. And that's also because of things like entropy. So, 200 years ago, when people wanted to make steam engines and stuff, right? You have to have a thermal source, right? So you burn coal or whatever, and you start boiling water, and then you make that boiling water turn some turbines and something, and then that makes the engine, the wheels of the train engine move, stuff like that, right? So what's happening is you would think of the boiler as a separate system from the rest of the train. And so that boiler is releasing heat. That heat is going into the rest of the train. And that's causing multiple things to change. It's causing the whole train to move. So we would think about the kinetic energy of the whole train. So 1/2 mv squared of the whole train. But it's also causing the temperature of the train pieces to change because the boiler is hot. So if you're in a train car near that boiler, it's going to be hotter. But we can see this in the motion of the train. Whereas this, you would have to start measuring the temperature of different parts of the train and see if those temperatures change. This, of course, is the part we actually want. This is why we have the boiler on the train. This happens and we can't really help it because of entropy. Does that help?
Yeah, kind of. But like, what if the system was bigger? Like, I don't.
So that's a real good point that I was delaying. There's nothing that tells you what you have to choose for your system. You get to choose your system and put the dividing lines of what's going to be inside and what's going to be outside. And that could be all the way down to like a single particle or the entire universe. Right? So at some point, you have to make some sort of call. And in this class, I tried to guide you to the choices that are going to make the problem easiest to solve. But there's definitely not just one choice that could be made. There's technically not infinite, but pretty close to infinite options that you could choose. And if you just include the boiler in the train in the system, right? I was suggesting keeping it outside the system and have it act on the train. It is on the train, so it could make sense to include it. Well, now the math that you have to do your calculations has changed. Because now you are turning a chemical energy into a thermal energy directly. Now you have to think about the chemical energy release, which fortunately that's not super hard to do in that specific case. And see how that chemical energy, some of it is becoming thermal, and some of it is leading to the motion of the train. So trying to figure out where to draw that line helps you get to a problem that you can actually write down answers to. And so strategically, you cut out the things that you can't measure very easily. And, you can usually, it is easier to calculate the heat flow from a boiler than it is to calculate the chemical energy changes due to the combustion of the coal. Is that, this is an aspect of my nature that I recognize makes it hard for students, is I don't like to make an answer simple enough that it excludes the correct answers. Right? Yeah. And hey, that's what science is, right? The more information you have, the more questions it leads to. Yeah, we did that one. Okay, so this is a statement of the math that's going on behind the scenes here. I'm going to focus on these first two rows initially. This is looking at the total energy in a system. And we just use the letter E for that. That one at least makes sense. And you get the total energy of a system by adding up all the kinds of energy that you could have. So maybe you've got kinetic energy in your system. Probably you do. Gravitational potential energy, spring potential energy, thermal energy, chemical energy, nuclear energy, electrostatic energy. All these different kinds of energies, many more than what you see written down on the screen right now. So this top equation is hard to use accurately because we have all these other types of energies that we don't know how to even think about evaluating. But the next line is easier to deal with. On the next line, we're looking at changes of energy. And to get the change of energy, we just look at the change of each of the types of energies we just looked at. So we have change in kinetic, change in gravitational potential, change in spring potential, change in thermal energy, change in chemical potential. Well, it is chemical potential energy, but I wanted to say chemical energy. Change in nuclear energy, change in electrostatic energy, all these other types of energies also. But this equation is useful because if there are types of energy that aren't changing, their delta E is 0, we can just ignore them. It doesn't affect what we're doing if their change in energy is 0. So unless you have an atomic bomb in your problem or something, right, you don't need change in nuclear energy, because the change in nuclear energy will be 0. If you don't have moving charges, you don't need your electrostatic energy. So the change in it is going to be equal to 0. And so these are the terms that I give you, and actually on the equation sheet, I don't even include the chemical energy because most examples we're going to end up solving, it's not going to be a change in chemical energy either. And so this is basically the definition of delta E, how we figure out what delta E is. This, the first law of thermodynamics, is telling us how delta E is changing. So what's causing a change in energy? Well, it's if we have some work or we have some heat, or, combination. So putting these two things together, these are going to be our major equations for this chapter, basically. I'm going to type them over here. They're going to be on the template when we use a template. Yeah, well, it doesn't matter because I'm doing an equation. So delta E is defined. It's not a defined. So I'm going to use colon equal because that means that's one way of writing defined as. So this is change in kinetic energy. This is change in gravitational potential energy. This is change in spring potential energy. This is change in thermal energy. And I'm actually going to stop there because, like I said, we're not going to actually solve problems with changes in chemical energy. And then the change in energy is equal to work plus heat. The way we end up using this is combining them. Right? So we would say on the left-hand side, we've got all of those energy terms, and that's equal to work plus heat. And in this class, heat is going to be 0. So I'll go ahead and erase it right here. But that's just because types of problems we're going to see. We haven't actually defined mathematically what this is. We're going to have equations for every single one of these terms. Actually, I say every single one. We're not going to have an equation for that. But all the other ones, they're going to have equations. And we'll see them as we get there. Yeah, I'm going to skip that one. Okay. You have done this exact calculation, but just as a reminder, I want you to do this. We've got a van, a 1,200 kilogram van. It's going at 20 meters per second. I would like you to tell me the kinetic energy and what units does kinetic energy have? Exactly, joules, capital J. It's pretty big, yeah.
Do you ever listen back to your lectures?
I don't think so.
Specifically, do you know if you can hear your students talking?
Oh.
Like, can the recording hear?
I don't know for sure. I don't think so, since I'm not using an external mic and it's just directed at me.
Incredibly unfortunate.
It is, isn't it?
Still entertaining. Not that you're boring.
It'd be finally bearable to watch these videos.
I had said something to Dr. Berg one time, and I felt really bad. We were in class, and we still had like an hour left, but it felt like the class had been like was almost over. And I'm like, man, we still have an hour in here. The look on his face, I felt so bad. I'm like, I swear this is not what I meant.
So 240,000 off by 10 there. Got the idea. So these are the units. This was the units for momentum. So a joule is equal to a kilogram meter squared per second squared. If you just want to see the relationship between them, but that's what we got. Okay. Now, we are going to look at the change in kinetic energy. So remember that any change is equal to final minus initial. And the mass we had was 1,200 kilograms, and we just calculated that Ki was 240,000. Oh, sorry.
Oh, wait, final. Yeah, yeah. Mhm. Alrighty. Favorite thing in my morning classes when I remember that I have an Alani or a Dr. Pepper in my backpack, and the absolute joy that I feel. It has a picture. Do you prefer your fifth period or?
Why does everyone keep asking?
Did your fifth period ask question?
Yeah.
And you also have like 23 million kids in that class.
It is a lot bigger.
I think the obvious answer is this class.
100%.
I don't even think we need to ask.
They're so much more
I
fun.
don't know. They're hating my class. And we were supposed to be hated for period.
That's a hatred for the period, not the people in the class.
Yeah.
I think it's a mixture.
Are we more
A mixture.
lively than them? More fun.
I bet because they have class in the morning.
Yeah, but you also think like one of the biggest
Okay.
friend groups in the school. Like half of them are in that class together.
So this is correct.
Oh, wow.
It is negative because we're slowing down, right? So the amount of energy in your motion has decreased if your motion has decreased. Okay, so we're going to talk about specifically this term right here, which we're going to be using to calculate changes in energy. And so this is work. Remember, work is transfer of energy due to external forces on a system. And there is an equation for it. So I guess I'll write it out here so I can talk about each thing. So I write it. So we have F D cosine theta. So F F, I'm gonna have to turn off strike through, is the magnitude of the force. So since this is a magnitude, i.e. just the number of newtons, but no sign.
I know ETC or ECT, whatever it is, transfer, etc. What is ID?
Stands for ist-est, which is to say, which I think, or est, I don't know, it's Latin. It means for, like, that is, basically. So it's,
So it's the same thing. So it's the same thing as like
Oribe, I think.
Yes.
it's the
Oribe.
Orion. So it's pretty much the same thing as I forgot where I was going with that. What did I ask? Oh, for example, it's pretty much the same thing as for example.
it's not. So, so e.g., which is exempli gratia, or some, again, it's Latin. I don't know for sure if I'm saying it. It might be gratia or something. Anyway, that one is to give examples, or give an example, maybe. Again, it's Latin. But that's what it's doing. IE is restating something a different way.
Okay.
Oh, it means that is. Well, I gotta try to remember that.
I already explained that.
Hmm?
What is it?
What you said?
I already explained that.
I would expect. Is that what you said?
I expect that.
Ooh, yeah.
She's asking about Pig Latin.
SC. Italy.
Why do you all do that so quickly?
I watched the thing go.
I'm in Innsbruck.
And then we was
And I asked a question.
it's like, if they do it, I can like, if they do it, what is it? If it is.
My friends and I used it in class like 24/7. Yeah.
Too many rules.
Yes, I know it's past due.
You
On my to-do list, leave me alone.
Okay, but it makes me upset. But why can't we all just try to one rule?
Oops.
I never heard anybody say the rules different.
Like some people don't think that if the letter starts with a vowel, they don't say that word in play. They just move it to the end.
I used to say if it starts with a vowel, I've always heard if it starts with a vowel, it's just the word A at the end. If it starts with a consonant, you take the consonant off the rest of the word and then the consonant.
I see people like move it to the back.
What if it's like an SC?
You move that and
Both.
both.
I don't think you've just given up with like talking. And
That's okay. The people who are going to watch the video will still.
Teach them
That- Okay. So, actually, this part's going to be hard for the video. Should I consider Becca's request for slightly early dismissal?
Yes.
Yeah. Just because the demo is going to be hard to video with what I have set up.
Girl.
Okay, so live video.